Ladies and gentlemen, please welcome the General Chair of Frontier in Optics, Alex Turrican.
Good morning, everybody. How are you doing this cold morning? I came from sunny New Jersey, and it's way too cold for me. Welcome to Frontiers in Optics and Laser Science. This conference is our connecting point for our community of optics and photonics. And we cover a wide range of topics from research to industry, from science to applications. Attendees from more than 50 countries are here this week. And that includes volunteers who served on Optica Board of Directors and governance committees, and leaders who represent more than 75 Optica student chapters. Before we start our program this morning, I would like to thank my General Co-Chair, Lin Kai Kao. Unfortunately, he cannot join us this week. I would like also to recognize the program chairs, program committee members, theme coordinators, and leaders from Optica technical groups for their efforts and work in coordinating of this conference. The technical sessions and show floor programs that you are going to see this week is basically a result of their hard work and dedication. We also acknowledge support from our corporate sponsors and exhibiting companies whose financial assistance helps to make Frontiers in Optics possible. And to our co-sponsors, Optica and APS Division of Laser Science, we would like to thank you for your continuous support and providing our community with this opportunity to meet and to connect. So please join me and let's give them a round of applause. Thank you. Thank you. UNESCO has proclaimed 2025 is an international year of quantum, as you know, marking 100 years of quantum mechanics since it was first developed by Werner Schrödinger and Werner Heisenberg and Werner Schrödinger. Optica and APS are proud to be co-founding partners and supporters of this international year of quantum in recognition of transformative potential of quantum technology. And as you know, this year, this potential was reflected in the Nobel Prize in Physics that was given to 3 scientists in the area of quantum mechanics. So let us learn more about this global initiative to celebrate quantum science. And now I am pleased to welcome Optica past president and chair of Optica Foundation, Eric Mazur.
Thank you, Alex. Frontiers in Optics and Laser Science celebrates the advancement of science and its fulfillment in application. In a time of fast-moving technological change, when familiar products like automobiles and glasses are on the edge of amazing reinvention, and virtual space becomes as normal as the physical, this conference brings forward true visionaries to speak about what is to come. But we should remind ourselves that discovery is not new. It's incremental. It builds on the shoulders of past innovators. FIOLS creates an intersection between early career professionals and established researchers, all sharing the common goal of making an impact and generating innovative ideas, two of Optica's core values. It's a unique event that encompasses a wide range of topics representative of Optica's 8 technical divisions and 50 technical groups. Whether your interests lie in quantum technologies, sensing, space optics, or machine learning, you're an essential member of our global community and a welcome participant to this meeting. And speaking of Optica technical groups, I'm pleased to celebrate the work of 5 of them for their outstanding efforts this year. Please hold your applause until we've recognized everyone. For most active technical group, the award goes to the Non-Imaging Optical Design Technical Group, chaired by Marina Meretska. For most information shared, we recognize the Short Wavelength Sources and Attosecond High Physics Technical Group, chaired by Balázs Major. For most popular activity, we recognize 2 groups. First, multifunctional meta-optics, hosted by the Holography and Diffractive Optics Technical Group, chaired by Ivan Divlyansky. And second, how to use SMD tool to design and simulate meta-lenses, hosted by the Non-Imaging Optical Design Technical Group, chaired by Marina Meretska. For greatest growth in activity, the award goes to the Tissue Imaging and Spectroscopy Technical Group, chaired by Katarzyna Komo-Libus. And the Innovation Prize goes to the Optical Fabrication and Testing Technical Group, chaired by Christopher Holmes. To each of the technical group chairs, please stand and be recognized. I hope they're here. Well, let's give them a round of applause anyway. We thank them for their valuable work to the community. And now, we would like to take a few moments to pay tribute to some of the colleagues we have lost this year. In the time they had, they filled our lives with much friendship and joy. Each of them made significant contributions to the science of light, driven by their curiosity and their expertise. Their work will endure and remind us in our daily moments of just how fortunate we were to have them with us. Their contributions will forever impact our profession. Thank you.
Thank you, Eric. And now we are moving to technical part of our session with 2025 FIO plenary speaker, David Wineland. Since his school years, David was passionate about three things: mechanics, mathematics, and of course physics. And these three lifelong passions have shaped his career. And that led him to the field of large-scale mechanics and ultimately becoming an experimental physicist. And his passion for mechanics and physics naturally converged and culminated in when he won the Nobel Prize in Physics for manipulating and measuring individual quantum systems. David is currently Philip Knight Distinguished Research Chair at the University of Oregon. He published more than 730 papers that have been cited more than 85,000 times. It's a remarkable achievement. He has been recognized for many awards, including that he was elected as an Optica Fellow and honorary member of Optica. This is the highest honors in Optica. So please join me in welcoming our speaker and Nobel Prize winner, David Wineland.
Well, thanks very much for the nice introduction. And as you see from the title of my talk, I'm talking a little bit about Schrodinger's cat, and in fact, how it leads to some things we're interested in these days, like quantum computing. Let's see. Yeah, so why are we interested in this? And I guess I already mentioned this, that, I think first of all, it's an interesting thing about Schrodinger's cat is an interesting way to learn about the basic ideas of quantum mechanics. And as I said, that we're interested in several applications. For most of my careers, I've been involved with atomic clocks, and these days there's a lot of interest in quantum computing as well. So going back a little bit, the United Nations General Assembly proclaimed that 2025 as the International Year celebrating 100 years of quantum mechanics and to promote the field. And in this talk, I'm going to talk a little bit about my part along these lines with many great colleagues. And so I span maybe the last 60 years of this 100 years we're talking about in terms of my work. So just to summarize, I'm going to just introduce kind of the weird things about Schrodinger's cat, and I'll say, then give an idea how we can manipulate quantum states for example, for computers and other examples. And I am going to be talking about using trapped ions for this purpose. And I have to give my apologies to the experts in the audience because you're not going to be learning very much. So this is more geared towards the students that are, coming up, and they'll be the future of our field. So anyway, a nice example I liked was given by Fred Ellen Wolf, you see cited down below. And what I like about this is I think it gives the ideas of superposition and quantum measurement without people having to know anything really about quantum mechanics. And so the idea here is that in the upper right-hand corner, there's this box, and at certain times you can you can think about, you know, the one, say that this face being in the foreground, and at other times maybe you'll picture this face being in the foreground. And in some sense, the box has both properties at the same time, and this is very much like superposition. The other thing, when you tend to see one face be in the foreground or another, one orientation or another, this is very much like doing a measurement. So I think this is a really good example to superposition and measurement in quantum mechanics. And so the idea is that when we see one view or the other, that's very much like collapsing a quantum state into one of its eigenstates. So what about data storage? And of course, we know in our classical computers, we store, we store bits as zeros and ones. And in the quantum world, we can think about superposition. So in some sense, just like the box, we can store both zeros and ones at the same time. Okay, so anyway, you see in a measurement then, is we have a superposition of two quantum states. When you know, it can, in superposition, and then when we measure, it'll turn out to be one state or the other. So how does this scale? Of course, for a classical computer, we know how it scales there, but in a quantum computer, it scales, the memory capability scales exponentially. So for example, for a 3-bit quantum register, it can generally be in a superposition state, so there's 2 to 3 states or 8 states in this case. And so if you think about scaling up, though, for 300 quantum bits, it stores 2 to 300, about 10 to the 90th numbers simultaneously. And this is a larger number of information slots than if we took all the classical information of the universe and put it into one register. And of course, the other nice thing is that in the quantum world, when we operate on one qubit, say flip one of these qubits in this 8-bit register, it basically, in general, since all the coefficients in front of this wave function are different, then it basically changes all those coefficients at once, just flipping one bit. But of course, when we know that or the other thing is when we can think about doing a lot of parallel processing on this superposition. But of course, we have to remember when we actually measure the final state, we're going to get one number. So we have to live with that restriction. And so actually, of course, these things were known for many years. And what really set things going, at least in terms of quantum computing, was that I think many of you know in the mid-90s, Peter Shor, a quantum theorist, he came up with an algorithm for factoring large numbers. And I'll say just a little bit about it. But this was one reason it would be so interesting is that basically the most common form of encryption systems derive the security, like RSA, derive the security from the inability to factorize large numbers. So that's why his algorithm had such an impact on quantum computing. And just to give you an idea, so to compare again with a classical system, we know the two gates we can make a general computer out of, or say a bit flip and then say a 2-bit AND gate. In the quantum world, there's an analogy. But because we're dealing with superpositions, rather than think about bit flips, we think about rotations. And the simplest thing for me to think about is if we have a spin 1/2 particle, and its orientation is somewhere located on the Bloch sphere, then and the general operations we can do are these rotations of this fictitious spin 1/2 particle, as you see on the lower left. And for example, a 2-bit logic gate that is universal is just a simple so-called phase gate, which I show the truth table down below there. So for example, if we apply this lower phase gate, and if we have a superposition, a product state of 2 qubits, in general, when we apply this phase gate operator, we get entanglement. That is, we can no longer, after we apply the gate, we can no longer write the total state as the product of the 2 separate states of the 2 qubits. So anyway, basically some earlier work thinking about using quantum systems for computers comes from Richard Feynman and David Deutsch and Paul Benioff. And they were thinking about using quantum system like spin 1/2 particles, but what really set the things on fire was that Peter Shor came out with this very efficient algorithm for factoring large numbers. And of course, this was RSA, for example, derives its security from the inability to factorize large numbers. So this had a big impact, and certainly was important for people doing quantum encryption. And actually, we had started playing with some of these ideas in our lab, and this was the only time in my career when normally when you think about trying to develop a project, you go to Washington, try to sell your ideas to the project leaders there. And this is the one time in my whole career when NSA came to us, and they knew about what we were doing, and so they were eager to help us carry on our work. And so anyway, just to give a more general picture, so the kind of thing Peter Shor was dealing with was coming up with a much more complicated system. So we might have a large register which would register, for example, could hold the number we're trying to factorize. And then we basically apply a series of 2-qubit gates. This is Shor's algorithm, and construct it in a careful way, both 2-qubit gates and single bit, the R's in that expression. And then when we carry out this algorithm and do a measurement, we come up with a number that it's not actually the number that we factorize, but it can be easily processed into giving the factors of the number we want to operate. And in some sense, this algorithm is very much, I think, a good analogy is like the 2-slit water wave experiments we learned about in classical physics, maybe in high school. And basically what we're doing is this Shor's algorithm is providing this very complex analog of this water wave interference experiment. And so that's what the function of these two and single bit gates, that they generate this water wave action. And so to give a number, a rough number, to factorize a 150 decimal number, we need about 10 to the 9 operations, and ideally they aren't good enough that we eventually have to think about error correction for these very large problems, but we can do some simple demonstrations without invoking error correction. So coming back to Schrödinger's cat, I think we all know this example that Schrödinger came up with. He was, of course, being one of the inventors of quantum mechanics. What I find, really interesting is he was dissatisfied with quantum mechanics, that because it would potentially lead to this bizarre situation, meaning his cat. And so his example was, suppose we have we put in a sealed box, a single radioactive particle, and then if the particle decays, it activates a mechanism which, inside the box is a poison capsule and a cat, and so when the particle decays, the idea is that it releases poison and kills the cat, but at some intermediate time, all quantum mechanics tells us is that we have a superposition of these two states shown on the bottom, where particles undecayed and the cat alive, and the particles decayed and the cat is dead. And as I say, I think this, my understanding of the history is Einstein, Schrödinger was really bothered by this, but in fact, this is the kind of thing we can think about these days. So in fact, he said, well, one way out of this, he says, well, we never experiment with just one electron atom or small molecules. In thought experiments, we sometimes assume that we do, but this invariably leads to ridiculous consequences, meaning his cat. And, but in fact, these are, at least for small numbers of particles, these thought experiments are now our world, and we can start to play these games. And basically, to be able to do this, we just need precise control and isolation from the environment. And this is easy to say, but this is the thing we're all trying to fight against in these kind of experiments. And so some examples I've been familiar with were atomic clocks and quantum computers. And of course, there's many people and groups around the world involved in this. A little bit more history from my side, or for atomic physics, is that Peter Shor came up with his algorithm in the mid-90s, and around that time, one of the big meetings in atomic physics is the International Conference on Atomic Physics, and that year it was in Boulder, Colorado. I was one of the organizers, and I knew Arthur Eckert pretty well. And anyway, Arthur Eckert understood Shor's algorithm, and we got him to come in and give us a talk at this meeting. And at this meeting, where for the ion trappers, was two of our favorite theorists working on trapped ions, and that's Ignacio Cirac and Peter Zoller. And so their idea for a baby quantum computer is the following. Suppose we have so our trap is this object up here. Basically, it's a three-dimensional harmonic well where we make the harmonic well along the axis fairly weak. And when we stack charged atoms, ions, into this trap, they all want to fall to the bottom of this potential well, but the Coulomb repulsion holds them apart into this regular array. And that's nice because it allows us to address these individual qubits in this array. And so we tend to initially think about the motion in this harmonic well classically, but in the end, we know it is harmonic to a high degree, so we have to think about the quantized energy levels. Anyway, their basic scheme for doing a logic gate, say between two atoms in this, two ions in this register, is the following. And again, what we're going to think about is the qubits associated with the internal states of the ions, but we can also think about a qubit between the ground state of a particular mode of motion and the first excited state. And so their scheme for realizing a two-qubit gate between two selected ions in this array is the following. First we'd freeze out the motion so that all the motional modes are in the ground state. And then we would, let's say we would, suppose we wanted, I should have started out and say, suppose we want to do a quantum gate between the internal state of this ion and this ion here. One way we can do that is we would first map the internal state of this first qubit ion onto the ground and excited state of one mode of motion. And then the second part of this would be that we would then do a gate between the motion qubit, which is now shared with all the ions, and the internal state of this second selected ions. And so the basic idea for this then is that how we can invoke this is that suppose we consider manipulating the internal states of the ions with laser beams. So in this case, the qubits are actually separated by an optical frequency for this example. And then we have to dress those levels with the individual motional states for a particular mode that we're going to use. And the idea of performing this gate then is that we would first map the internal state of this first selected ion. We map the internal state onto a superposition of the ground and first excited state of motion, which is then shared by all the ions in this array. And then the second step would be as we do spin motion gate between the internal states of this ion and the motion. And so the initial state of that ion it's got its internal state superposition, but it now also shares the motional state superposition. So their idea for one manifestation of the gate is, so these are the 4 levels we have to worry about of this second selected ions. And their idea was just to take a laser beam and do a 2 pi rotation on this, between these 2 states of the register using this auxiliary state here. And so this would give us this phase gate that we wanted to realize, and which also gave us the entanglement in this operation. And actually, we were Chris Monroe had come to work in our lab a couple of years prior to this, and we were starting to play some of these games, and we just happened to be in the right place at the right time. Peter Zoller and Ignacio Sirac was very nice to share their algorithm with us. And we had been playing all these games, and so literally within a few weeks we could implement their gate, and so we were able to do that. And this was one of the first publications. And then later, I mean, of course, we want to do it for a much larger case. And actually, the first people to extend this idea was Rainer Blatt's group in Innsbruck, and they did the complete Sirac and Zoller gate as they first described. And so there's different ways of looking at these problems, and I just listed a few examples. This one you have to wade through privately a little bit, but we can think of motion and sensitive gates. That is where we'll start out. Here's the two qubits we're trying to connect, and we go through some intermediate states, but I show some of the intermediate states here. And basically, we can realize this 2-qubit phase gate with these stimulated Raman transitions. I'm still assuming these are optical levels here. And so this is this kind of logic gate has become one of the mainstays, at least in the trapped ion world, for doing 2-qubit gates. Okay, what did I write there? Anyway, we can probe all the different hyperfine states with these by tuning properly. And in fact, for a large number of ions in the trap, we realize a more general spin-spin Hamiltonian shown here. And actually, it was just I think this was generalized more by Milburn and Schneider and James. In this paper that I've underlined there. And this is kind of the basic scheme that most of the ion trap groups have followed since. And just to give an idea of how these gates can be viewed, suppose we have this wave function which represents the motion in XP space. And basically what we do to invoke these phases that realize the gate is that we apply displacement. You can think of it as a successive number of displacement steps, but basically we arrange it so the steps will create a loop in phase space, and it turns out that the phase that's picked up is proportional to the area between those 2 states, and so we can make by tuning things we can make this 4-state dependent phase gate to realize the truth table you see at the bottom down. And this would be a general quantum gate between 2 spin qubits that we could extend from. We tend to use, in principle, we have done with this microwave forces and things, but we tend to think about using optical forces. And the idea there is we think about doing stimulated Raman transitions. So if we just think about one ion in the trap, is that these laser beams apply a gradient that we can do to apply this force and push the ions in a phase space in a loop. And so the way we do that, we think about crossing 2 beams where the frequency of the 2 beams is separated by a frequency near the motion frequency for particular mode. And so there's some interference pattern, but if the wave of the standing waves are, for the two forces are the same, then we think about standing wave, but what we do is we mistune the frequency slightly of these two Brahman beams, so that when we apply the gate, this intensity wave sweeps across the ions, and because of the gradient in the intensity, then we can force the circular motion of the ion that gives us the phase we want to be able to bring out the phase gate in this logic operation. We can think this is the case where if we use the stretch mode frequency, that is between two ions, shown in this view graph, and the idea is if we apply this standing wave, then we can tune it so that we excite only the differential motion, and then the common mode motion shown below is not excited. Anyway, this is the basic idea, how we separate that, the forces that apply these phase gate operations. And for anions, we more generally realize a Hamiltonian that looks like this JZ squared operation shown on the right-hand corner down here. And the advantage of this so-called Stark shift gates is that it doesn't depend on the initial motional state of the ion if the amplitude of the excitations is smaller than the effective wavelength of this Raman transition wavelength. And if the spread of the wave function is smaller, then we realize what's so-called the Lambdicki limit. So we can realize this idealized displacement gate that I described earlier. And it's the same picture for forces in other directions, say sigma z, sigma x gates. Anyway, this is from the basis for a lot of the work that goes on in the trapped ion world. Anyway, and we've done this with to give an idea that this is the performance not too long after these gates were realized. So you see, we got up to started approaching 3 nines in the around in the early 2000s, and then and we did this on optical qubits and hyperfine qubits in the ground state, and we could get up to about 3 nines. You can see in terms of the fidelity of the gates, and just to set the scale, we really want to get to 4 nines. But think about making a serious quantum computer. But anyway, this was a step in the right direction. One sort of curious thing, you can see the results from the group in England, and also our group. And actually, they came out at about the same time. And one little interesting thing that happened, usually in PhysRev letters, the editors will have a little write-up selling, some of the interesting ideas that are reported in the particular issue of the journal. And actually, they were nice enough to give us another 9 of fidelity, so we really lucked out there. Anyway, so what about scaling? And what we think about is just a very simple idea that if we get too many ions in the same trap, we just can't separate the modes well enough. So what we think about is having an array of ion traps where we will have a small number of ions in each group, in each register here. And then if we want to form a gate between 2 particular ions, we would basically move, say, grab onto an ion with optical dipole forces, move it into this lower array, and similarly pick off an ion from one of the other trap areas, and then bring them together to perform this logic gate. And then we could take them out and move them somewhere else to bring other ions into this area. And we typically, because we're moving the ions around, we need another ion to cool the ions down so they start in the ground state when we implement the gate. And we do that by having some other ion species. In our case, it was beryllium ion qubits and a magnesium ion that does the cooling to get us back to the ground state after we move the ions around. And these are just some of the first simple ideas of how we made these traps using 2 layers of electrodes. You can see up here to form the basic structure that we show over here. We sandwich 2 electrodes together. And these are just some of the examples that we realized early on for this. And we could also then make a more complicated structure where we could move ions around and change their places by moving into these vertical slots. And these are just some of the future ideas, scaling these ideas up, and I won't say too much about that, but basically we can scale up this 2-layer geometry up to very large sizes now. And a little bit more about topology as we can think about. Suppose we look down on this 4-electrode structure that I've shown. The idea there is to get the idea how it works is that we can, we can think about when we put these electrodes into a surface array, we can still realize this electric quadrupole configuration that's shown on the bottom. So we're looking down the axis of the system in this bottom picture. And this is just one of our early examples, very crude examples. And actually, this is one of the postdocs in our group, Jason and me, and I went to a much larger array. You can see here, we call it a racetrack for obvious reasons. And actually, there's some problems with it. It didn't work that well. But this was actually kind of at least the start of a basic idea that other people have grabbed onto. And anyways, the other thing is we could start to think about spreading entanglement throughout the system. So basically, we could entangle 2 remote ions via optical, making optical connections between, say, 2 ions in separate locations, and then using scattering from those particular ions, and then combining on a beam splitter. There's details that I'm not going through here, but basically this kind of arrangement allows us to entangle then the 2 states of these, in this case, ytterbium ions. Anyway, we can do things like teleporting gates between sites in the quantum processor, and we can also realize these basic ideas in a quantum communication network that we were able to demonstrate the basic elements of in that paper there. Anyway, the other thing that's been interested in by a lot of the groups is in doing more interesting simulations. So, for example, if we want to separate this more complicated Hamiltonian, we can use these basic ideas and just build up from using the basic operations I described. And this is a little bit out of date now, but it shows some of the groups working on these ideas to do more general simulations based on these Hamiltonians. So this was our group, and this is Rainer Blatt's group, and this is John Bollinger in our group at NIST, who was using a different kind of trap where the ions were arranged into a circular array. But the ideas are pretty much the same. And there's now many groups, there's about over 100 groups working on these basic ideas. And this is, I soaked this particular paper here because this is from Tracy Northrup, who's a member of Rainer Blatt's research group in Innsbruck. And anyway, if you're interested in seeing what everybody's doing, you can look up that reference there. And if you don't catch it now, I can give it to you later. Anyway, this just gives a sampling of the groups that we know about. They're seriously working on these issues, just using ion traps. And obviously, there's many other platforms. Certainly, a very successful other platform close to ions is to use neutral atoms held in optical tweezers. And they've done a lot of work. Of course, and one of the leaders in the whole business is using Josephson junctions. And that work continues still. And has progressed very nicely. So I would say there's no clear winner, and all these groups have progressed quite a ways in this. And so just kind of summarize here. One thing with our ion traps, we can maybe consider we can make at least smaller forms of this superposition. I haven't normalized it here, but we have equal superpositions of all the bits in the 0 state in equal superposition with all the ions in the upper energy state. And so one thing we can think about is for large N, we could take one of the first bit and move it into a separate region here, and then we could have this larger group of ions, which if they, you could argue if you build up the number large enough, we actually get a macroscopic superposition. And although it's a little bit cheesy, we would say and we could use some classical meter to measure the magnetization, like a compass in this larger sample. And so we would actually say this is very much like Schrödinger's cat, that is, we're entangling a microscopic object, this one qubit, with a more macroscopic magnetization in this system. And we would say this does have all the features of Schrödinger's cat, that is entangling a microscopic particle with a more macroscopic system. So what about the future? Well, we've been hearing a lot about computers, and I won't. There's been a lot of interesting stuff. So I'm just trying to give an overview here. But we're now getting down to, the gate. We'd like to get the gate operations down to about error rate of about 10 µ/4, and now several experiments are reaching this. And so, we can maybe think about this factoring machine, and I don't know, that problem may go away because people like NSA, they have other encryption methods, and to get around using RSA, and so anyway, maybe that problem will go away. But anyway, one thing we're looking for the future to be able to do these more complicated simulation problems, and one of our favorites in our lab in Boulder was that. Say, improve atomic clocks through these basic ideas. And I won't, of course, there's many companies doing this now. You can find them on the web here. And actually, I haven't looked up this reference lately, but this reference here, I can give it to you later. They tended to keep tabs on all the work going on in the area of quantum computing. And I would say, as I said, in my career, my career started, I was registered with Norman Ramsey in there. I was working on masers, and so I've always had an interest in atomic clocks. And one clock we developed at NIST was to use an aluminum ion so the clock transition would be this transition at 267 nanometers in aluminum, and the life. It's a fairly long excited lifetime, so we could get very narrow resonances on this clock transition, and we could detect the ions. Then, if we started the ion in the ground state, tried to excite it, and if we were off resonance, then we could drive this transition and see it. And if we hit the transition, then this scattering would go away. So that's how we basically detect transitions in this system. Unfortunately, in aluminum, this transition, the second transition, has an uncomfortably short wavelength. So basically what we did there was we developed what we call a quantum logic clock. And basically we would put in the same trap as the aluminum clock ion. We put, in this example, a magnesium ions. And what we could do with the kind of operations I briefly described is when we tried to drive this transition here, we could actually map the superposition of the clock transition into a superposition of this transition in magnesium, and this was at a much lower frequency that we could easily detect which state the ion of magnesium was in with a much easier laser to build. So anyway, this is just mapping this aluminum clock onto the states of the magnesium for easier detection. I obviously goofed up with my PowerPoint down on the bottom. Sorry about that. But anyway, we in this aluminum clock example, we're able to get a systematic uncertainty below about a part in 10 to the 8th, and this is kind of set the standard for precision and systematic uncertainty in some of the clock experiments. Also, just an interesting side thing I like to point out, Zhen Yi, our colleague at Chile in Boulder, Colorado, he's been doing similar things rather than with optical transitions. He's been looking at nuclear transitions, and he's done some, very nice experiments where he gets performance numbers very close to this. So he may be our main competition in the future. And the hard part of that is it's a nuclear transition, so it's hard to generate the wavelength that you need for the clock. But he's been able to do it, so that may be the future. Anyway, so the other thing is, we've been able to do some other kinds of things. We've been able to do Ramsey interferometry, but now entangling states of ions. And I'm running short on time, but basically I described how we could do Ramsey interferometry with 2 ions, with 2 states, but we can do it with much more complicated states. And anyway, I just wanted to say I'm now at the University of Oregon, and I'm working with David Alcock, and we started a small group there. And basically, we're trying to do these quantum logic operations, starting out with calcium-40 ions, and I won't go through the details here, but this was our first set of graduate students, and some of these guys have already graduated now and gone on to do their own experiments. But this is the kind of, so we're trying to spin this group, these ideas currently with atomic calcium ions. And these are some of our more recent additions to the group, and I'd like to, one thing we're working on. So this is the calcium system we're working on, and so just some of the topics where we've been able to realize, get experimental results on. I show here, for example, 4 and 6. The bottom here, I want a recent result. I'm using 4 and 6 photon stimulated Raman transitions to carry out some of these basic. These basic operations. Anyway, if someone wants the details of this, I'll be happy to send you these references. Anyway, that's pretty much it, and thanks for listening.
Thank you, David. It's very fascinating. Excellent review of fascinating area, and I feel your passion for this quantum science. Let us thank our speaker one more time. So that concludes our session today. Thank you very much for coming, and enjoy your weekend Frontiers in Optics. Thank you.